welcome to a tutorial on volumes. So the purpose of this tutorial is to introduce to you some of the most important three-dimensional figures and to then show you how to calculate their volumes. And by way of introduction and motivation, I think it is helpful just to quickly work up from one dimension, what we might call 1D, up to 3 dimensions, 3D, just to get this concept of how many products of a length you should expect when you're calculating a volume. So the one-dimensional universe is a line, and here's part of that universe. Here's a line, and it has a length L. So all one can talk about here is a line, and its length is L. Now in 2 dimensions, we have a huge, dazzling variety of different shapes. I just want to consider one here. I want to generalize my line, come out at right angles, and make a rectangle. And now we have a length, of course, and a breadth or width. I'll call it W for width. And we can speak of the area of this rectangle being a product of 2 lengths, the length times the width. An area must always be a product of 2 lengths. I stressed this in the circles tutorial when we were talking about the area of a circle being pi r squared. It's no surprise that there's r squared in the formula because the radius uniquely defines a circle, and so the area must be proportional to that length squared because you must have a product of 2 lengths. So in 3D then, we're going to generalize this. We're going to draw a cuboid, which is the 3D generalization of a rectangle. Here we are. Right. So I'm going to sort of imagine taking this rectangle and putting it on its face, and then that's going into the page, that dimension. So here's the width of our original rectangle, here's its length, and now I have a new variable which is the height of this cuboid. And we can speak of the volume enclosed within this figure, this 3D figure, and it would be the length times the width times the height, and that is the volume of a cuboid. The concept I really want you to get from this is that a volume must have a product of 3 lengths. So every formula that you see for a volume, you should be able to identify that there is a product of 3 lengths in that formula. So let's see an example of that straight away. Let's consider perhaps the most beautiful 3-dimensional figure, which is a sphere. And that's completely defined by 1 length, which is the radius of the sphere. So imagine that you have a point and you trace out in 3 dimensions every other point that's a fixed distance from your original point, and you will trace out the surface of a sphere. There's a rather crude drawing. There's the center, and there's the radius of that sphere. And the volume of the sphere must be a number times the cube of the radius, because a volume has to have a product of 3 lengths. We can completely define the sphere by the radius, so it must be possible to write the volume as a number times the radius cubed. And indeed that is the way that we write the volume of a sphere. So the volume we write as a constant times r cubed, and the constant has a rather beautiful form. It is 4/3 pi, or 4 pi divided by 3. And we can sort of compare that a little bit with the 2D equivalent, which is just a circle of radius r. And we know that for a circle, the area is pi r squared. So there's quite a nice comparison here that the r squared in 2D goes up to r cubed in 3D, and the prefactor, the constant, still involves pi. We get this additional factor of 4/3. One way to generalize a rectangle, instead of coming out at right angles and making a cuboid, you can imagine sort of rotating it about its axis, and then you would generate a circular cylinder. So here's a circular cylinder, called a circular cylinder because it has a circular base, and the volume of a cylinder is the base area times the height. Let me just write that in words first. So base area times the height. I've drawn it with a circular base here. Let's imagine that has a radius r for that circle in the base. The base area would just be pi r squared, and then times the height. And you often see this this formula written down for the volume of a cylinder. It's true if the base is a circle of radius r. And again, we have a product of 3 lengths in the volume, and it's obvious that h appears to the power of 1 because the volume of the cylinder will just increase linearly as we increase the height. So in a sense, you could argue from very basic principles that the volume has to be r squared times h and then times a prefactor, which is pi. Let's talk about another figure which is has a very nice formula for its volume, which is the cone. Let's draw a 3-dimensional cone with a circular base. So there we are, height h. And here, interestingly, the volume of a cone is 1/3 times the base area times the height. So let's say here that I have a cone that has a circular base. At this level of maths, when they're asking you to calculate volumes, things like cylinders and cones, I think they'll always have a circular base. These formulas of base area times height are true for any base, in fact, but I think it will be nearly always a circle that will be in the question. So let's assume this cone has a circular base. Then we have 1/3 for the volume is 1/3 times the base area, which is pi r squared, times the height. And that's really quite an interesting formula, because we could imagine that this cone is embedded in a cylinder with the same height and the same base radius. And what this formula indicates is that the volume of a cone is exactly 1/3 the volume of its enclosing cylinder. And that's true actually for any shaped base. It's really quite a beautiful property. It's also interesting to compare this formula for the sort of the 2D thing from which you could generalize a cone. So if we imagine a triangle, if we spin a triangle about its central axis, we'll get a cone, and the area of a triangle, as we know, is just 1/2 times the base times the height. And so you see quite a nice sort of connection between these formulas, that in 2D the area of this triangle is a number 1/2 and then base times height, and then in 3 dimensions the volume of this cone is a number 1/3 times the base area times the height. So you could imagine then saying, well, what about a 4-dimensional hypercone? Its volume would be 1/4 times the volume of the base, in quotation marks, times the height in the 4th dimension. So quite a nice set of generalizations here for cones. A figure very much related to a cone is a pyramid, which is really essentially a cone with a base that is a polygon. Let's just imagine we have a pyramid with a square base. Let me try and sketch this. So there's a square base. And that's not too bad. Okay, so there's my pyramid. Let's say the base has a length L there. Let's say it's square. And then let's say this pyramid has a height H. Then the volume of the pyramid is this 1/3 again comes in. So it's really just like a cone. It's 1/3 times the base area times the height of the pyramid. Right, okay, so I'm going to put this L squared in brackets just with that one to indicate that those are base areas, okay, which I'm actually even going to sketch in red just so you can really get a sense that it's just 1/3 base area times height, 1/3 base area times height. So that's sort of it. Let's just do an example to put some numbers in. Let's imagine we have an ornament which is a pyramid, why not? Okay, so we have a square pyramid. I'm going to draw this a little bit bigger. Whoops, that was not very good. Kind of missed where that was going then. There's a pyramid, and this ornament has inside it, so let's say that's a glass pyramid. Inside it, floating is are 2 spheres. Why not? I'm being very imaginative here with my ornament. So there are 2 spheres floating, as it were, in, not really floating, but encased in the glass of this pyramid. And each sphere has a radius equal to 1 centimeter. So they're not terribly big. And this is like a mantelpiece ornament. Let's say the square base has a side of 6 centimeters, and let's say it has a height of, I don't know, let's say 10 centimeters. And let's say that those spheres are made of wood. So this, we have spheres made of wood, and we have a beautiful glass pyramid, and we have to calculate the volume of the glass. And the volume of the glass will be the volume of the pyramid, take away twice the volume of a sphere, because those spheres are identical, and they're made of wood, so they won't contribute to the volume of the glass. So you often get these kinds of questions in the Scottish exam system where they'll ask you to calculate the difference between 2 volumes. That's always trivial so long as one volume is contained within another. If one of these wooden spheres was sort of somewhat sticking out of the glass, this would become a very difficult problem actually. But as long as they're completely enclosed, it becomes trivial, because we just have to work out the volume of the pyramid and simply then subtract, in this case, twice the volume of a sphere, because there are 2 such spheres inside the ornament. So, volume of the pyramid, well, it's 1/3 times base times height, so 1/3 times base. Well, the square base has a side of 6, So it's times 6 squared times the height of 10. I'm just going to use my calculator only because when we do the spheres we're going to have pi hanging around, so the numbers are going to get messy anyway. But this is obviously 36 times 10, which is 360 divided by 3. 120. This calculator is very old and it likes to play tricks, so it keeps me very alert. Actually, that's good to have a computer which is somewhat, malicious. A bit like that computer HAL in the famous movie Space Odyssey. This is far less intelligent than HAL, though. Although it will have heard me say that and be even more impish now, I suspect. So the volume of a sphere is 4/3 times the radius cubed. Here the radius is just 1, so that's not going to be too difficult. So that's fine. So that's obviously just 4/3. Interesting, isn't it? How much bigger the volume of the pyramid is compared to those little spheres there. So this is actually really going to be quite modest. This is literally 4/3 centimeters cubed. Let me write that to one decimal place, 1.3. Oh, I must apologize. I thought that was rather too small, and it's because I'm making jokes about 2001 Space Odyssey. What have I forgotten? Pi. Volume of a sphere is 4/3 pi times the radius cubed. So this is 4/3 times pi centimeters cubed. So 4 times pi divided by 3 is 4.2. That's what you get for doing maths and trying to be a comedian at the same time. Not a happy combination. Right, so the volume of the glass equals the volume of the pyramid, which is 120.0. I'm just going to try and keep everything consistent with decimal places. 120.0, and then I have twice the volume of a sphere, which would be 8.4 to one decimal place. And so I have 111.6 centimeters cubed for the volume of glass to one decimal place. So yes, so a little bit of an adventure doing that problem there, but I hope that you see that in fact it's really not too difficult at all. It looks terrible at first because you think, oh my goodness, the volume of glass, we've got these spheres and whatnot, but when you realise that you're really just subtracting the volume of a pyramid, you're subtracting from the volume of a pyramid some volumes of spheres, then you see it's really quite a simple problem. So that's volumes at this level of maths. There are some beautiful methods to calculate volumes of more complicated three-dimensional figures, but you need something called calculus to calculate those, and calculus in a way is just a tremendous, it's like a tank, compared to, this might be seen as a bow and arrow. Calculus was invented in the late 1600s and is an extraordinarily powerful set of tools in maths, and one of its many applications is to calculate the volumes of more complicated shapes. So if you proceed with maths for a few more years after this level, you'll certainly learn calculus and be able to employ that to do more complicated calculations. But still here there are some very important concepts, and the most important thing to get across is that a volume in 3 dimensions must be a product of 3 lengths, and therefore always you will be expressing your volumes as the cube of the relevant unit, here centimeters cubed. Right, I hope that was helpful, and I'll see you for the next tutorial.